Question number 36. The three combustion reactions are given. So we have been given three reactions in which the hydrocarbons are subjected to combustion and the energy liberated is also given to us. So the examiner is interested in which reaction the hydrocarbon has the highest calorific value. So if we talk about the calorific value, students, we know that calorific value is defined as the heat liberated per gram of the substance which is undergoing combustion. So if we talk about the molar masses of the species which are given to us, we have C2H6, we have C2H4, and we have C2H2. So if we talk about the molar masses, the first compound has a molar mass of 30, the second compound has a molar mass of 28, and the third compound has a molar mass of 26. So all that is left now is to divide the heat liberated upon the total grams, and we can find out the calorific value directly. So if we talk about the first compound, we have a heat of 1561, and this much heat was liberated by the combustion of 30 grams of the hydrocarbon. So this gives us a value of equal to 52.03 approximately. If I talk about the second reaction now, in the second reaction, we have a heat liberation of 1410 kilojoule per mole, and this is liberated by the combustion of 28 grams of the hydrocarbon. So this on simplification gives us a value of equal to 50.36 approximately. And if we talk about the third reaction now, in the third reaction we have a heat liberation of 1310 kilojoule per mole, and this heat is liberated by the combustion of 26 grams of the hydrocarbon. So this gives us a value equal to 50.38. So the examiner is interested in the species which has the highest calorific value, which means that the examiner seems to be interested in the species which liberates the maximum heat per gram of the substance undergoing combustion reaction. So we have to select the first option as the correct answer to this question. Let us look at the next question now. Question number 37. In the following conversion, so we have been given an alkyne which is allowed to undergo reaction with some reagent to form the alpha beta diketo compound which is given in the product side. So if we talk about the first reagent, H2SO4, HgSO4, so it will cause the formation of a double bond at only one of the two positions where the triple bond was present. So this is the hydration reaction of the alkyne, and this will not lead to the formation of an alpha beta diketo compound. If you talk about the second reagent now, the reagent given to us is reductive ozonolysis followed by reaction with water. So this option is correct, students. The ozonolysis will lead to the formation of an ozonide which will break the two pi bonds which are present and convert them into the alpha beta diketo compound which is given to us in the structure. If you look at the third reagent, NaOH cannot bring about this conversion. And if we talk about the fourth reagent, MnO2, it causes allylic oxidation. So this is also not the correct answer. So in question number 37, we have to select the reagent which can bring about the above conversion. So this can be achieved by the reductive ozonolysis which is given to us in the second option. Let us look at the next question. Question number 38. In the given sequence of reaction, so we have been given a cyclic alkyl halide which is allowed to react with KOH, MEOH heat. So this is the alcoholic KOH condition, students. This will lead to the formation of an alkene. So the compound A is going to be a ZF alkene which is represented by this structure. Now this compound A is allowed to react with BH3THF in presence of H2O2OH-. Now this compound A is allowed to undergo hydroboration-deboration reaction to form compound B. So the hydroboration-deboration, let's call it HBO-DBO. So the HBO-DBO is going to convert it into anti-Markovnikov alkene without any rearrangement of the carbocation. So this is the product B which is formed. Now this B is allowed to react with Na. So the Na will create a negative charge on this oxygen. It will liberate H2, leading to the formation of an alkoxide ion. And this alkoxide ion in the next step will attack on the ETBr which is given to us by an SN2 mechanism, giving us an ether. So this is the major product C which is formed at the end of the above reaction sequence. So for this question, we have to select the first option as the correct answer. Let us look at the next question now. Question number 39. In the given reaction sequence, the end product C is. So we have been given cumene, which is first allowed to react with oxygen, and followed by hydrolysis. So we know that this is the preparation reaction of phenol. Upon reaction with oxygen, the cumene will lead to the formation of cumene hydroperoxide. And upon hydrolysis, the cumene hydroperoxide will lead to the formation of phenol along with acetone. Now, it is clear to us that the compound A is phenol, whereas the compound B is the acetone, as mentioned to us in the question. Now, the examiner seems to be interested in the reaction of phenol with acetone in presence of HCl. So, if you talk about the reaction of phenol with acetone, so the acetone will accept the H plus from HCl, leading to the formation of a carbocation at the secondary position, which will get attached to the phenol at the para position. So the first equivalent will be added in this fashion. Now further, the OH group will attack to another H plus from HCl, which will convert this OH into OH2 positive and make it leave. So carbocation will be generated at this position, and which will add to the para position of another phenol molecule. So we're going to have the formation of this structure. Which is the major product C, which is formed in this reaction. So students, for this question we have to select the first option as the correct answer. Let us look at the next question now. Consider the given projection formulae. So in these four structures we have been given different methods of representation of chiral compounds. So if you look at the first and the fourth structure, they are given to us in the Fischer form. The second one is given to us in the Sawhorst form, whereas the third one is given to us in the Neumann form. So the examiner seems to be interested in which pair of compounds represents a pair of enantiomers. So if you look very carefully at the second structure, students, in the second structure, the position of the amino group is shifted. So in the first, this third and the fourth structure, the amine group is linked at the carbon where the methyl group is present. So this is a positional isomer. So we can rule this directly out of the equation. So we can eliminate options 1 and 4, as 2 will not be a stereoisomer of the other 3. So if you look at the other 3 species which are given to us, we can see that the first and the fourth are already in the Fischer. So we just have to convert the third structure into the Fischer representation. So to convert the third structure into the Fischer representation, we can first have an eclipse form. So the third structure can be represented as we have not disturbed the chiral carbon which is hidden. So we have Cl, Et and H at their respective positions where they are present in the original structure. Now we have rotated the front carbon by 180 degree. So the methyl group will reach the bottom. The H which was present at the left will now be present at the right. And the NH2 which is present on the right will reach up till here and it will be present on the left. So this is the Neumann representation. We have just rotated the front carbon by 180 degree. So now this can be converted into the Fischer projection. So if we convert this into the Fischer projection, we're going to have Me, Et on the vertical line. We're going to have H and Cl on the right, and we're going to have NH2 and H on the left. So this is the Fischer projection of the third structure. And if we compare it to the fourth structure, we can see that the fourth structure is not a mirror image of the third structure. So fourth is also ruled out. In the fourth structure, the H are present at the same side, whereas in the first structure, the hydrogens are present at the opposite side. So in this structure also, the hydrogens are present at the opposite side, and first and third are going to be enantiomer to each other. We just have to rotate the first structure in the plane by 180 degree to get the structure. So we can try and confirm that as well. So we just have rotated the Fischer projection by 180 degree. So Et will reach at the top, Me will be at the bottom, and H and H2 will now be on the right, and Cl and H will now be on the left. So this is the first structure. And we can clearly see that the first and the third structures are non-superimposable mirror images to each other. So these represent a pair of enantiomers. So students, we have to select the third option as the correct answer to question number 40.